Hi everyone. In this lesson, we will be discussing about the various applications of the integration process. Basically, we will be covering three applications of integration. First is in finding the equation of a curve. Second is its application in analyzing the motion of an object. And last is in computing for the area bounded by a curve and by a major axis in the Cartesian plane. Now let's start our discussion with how we can find the equation of a curve through integration. In your differential calculus class, you were given a function of x, and then you were asked to get the derivative of this function of x. What this points out is that if y is a function of x denoted by capital F of x, then its derivative, or the derivative of y with respect to x, is also just a function of x, denoted by small f of x. Now, in our integral calculus class, you will be doing the reverse of what you did before. You will now be given the derivative of y with respect to x. This equation is called the differential equation, since this equation involves one or more derivatives of a function. From this equation, you will need to perform integration in order to get the function of x corresponding to y. For us to proceed with the integration process, we first need to cross-multiply dx to the right side of the equation. By doing so, we will now see the integrating variables for each side of the equation. The left side will now be integrated with respect to y, while the right side of the equation will be integrated with respect to x. The result of the integration process will now result to y equals a function of x, denoted by a capital F of x plus c. The equation for y, or this equation for y, is called the family of solutions for the differential equation that we have just solved. It is also referred to as the general solution of the differential equation. The reason why it is called a general solution is that there are various possible finite values that we can substitute for the arbitrary constant c, which can still allow us to arrive to the differential equation dy over dx equals f of x. Now let's use the example in our previous slide to illustrate how the family of solutions of a differential equation looks like. If we are given the derivative of y with respect to x to be equal to 2x minus 4, then by process of integration, y will be equal to x squared minus 4x plus c. If we attempt to sketch the graph of y equals x squared minus 4x plus c, it will look like this. The graph of the general solution of a differential equation is called the family of curves. Now you may ask, why do we use the term family to collectively refer to these curves? The reason for this is that just like in a real family, you can identify members of the same family by their surname. In the general solution that we have just obtained, we may refer to y equals x squared minus 4x to be the surname of the family of curves, while the arbitrary constant c refers to the first name of each curve belonging to that family. Just to illustrate my point, this is the curve for y equals x squared minus 4x plus 0. This is the curve for y equals x squared minus 4x plus 1. This is the curve for y equals x squared minus 4x plus 2. And finally, this is the curve for y equals x squared minus 4x plus 3. Now what if we want to just call out one member of the family of solutions? Let's say I'm just interested with this curve, which corresponds to y equals x squared minus 4x plus 1. How will I be able to determine the value of the arbitrary constant c? If you are just concerned with one member of the family of solutions of a differential equation, then what you are trying to determine is a particular solution of that differential equation. And for us to determine a particular solution, we must set boundary conditions which apply to the particular solution that we are trying to determine. To illustrate how boundary conditions help us in determining a particular solution, let's go back to the general solution corresponding to this family of curves. One boundary condition that is true for the particular solution that we are trying to find is that when x is equal to 1, y equals to -2. You can see that the curve of the particular solution that we are trying to find passes through the point 1, -2, which is the boundary condition that we have just set. So by substituting the values of x and y stated in the boundary condition to our general solution, we will finally be able to compute for the value of the constant c. And by substituting this value of c to our general solution, we will finally get the particular solution that we are concerned of. A good question to ask is how many boundary conditions are needed in order for us to determine a particular solution for our differential equation. The quick answer is that it depends on the order of the differential equation that we are given. The order of a differential equation corresponds to the order of the highest order derivative appearing in a differential equation. Now let's give three examples of a differential equation and determine their corresponding orders. Let's say we are given y prime equals 4x squared. Since the highest order derivative appearing in this equation is the first derivative of y with respect to x, then what we have is a first order differential equation, and we only need one boundary condition for us to define a particular solution for this differential equation. Let's give another example. Let's say we are given the second derivative of y with respect to x equals 1 minus x. Since the highest order derivative appearing in this equation is the second derivative of y with respect to x, then what we have is a second order differential equation, and we need two boundary conditions for us to define a particular solution of this differential equation. Last example. Let's say we are given the third derivative of y with respect to x equals 2. Since the highest order derivative appearing in this equation is the third derivative of y with respect to x, then what we have is a third order differential equation, and we need three boundary conditions for us to define a particular solution of this differential equation. Now that we have presented the basic principles needed for us to obtain an equation of a curve, we will be presenting two examples in the next videos to demonstrate how to use these principles.